Alright, so in this video, I thought we'd focus a little bit less on the intuition and more on graphing the cosine and tangent functions, since we got a little bit further into intuition in the last video. This time we'll just be doing some graphing and maybe explaining some of it. Alright, so this time we're going to be doing a function of cosine of x, where x is some angle in radians. So, how do we start? Well, I think even though we're sticking to a little bit less intuition and more just hard calculating, that's a little bit too long. I think I'll stay with the graph. I like that format. So, let's start at 0, I guess. Why not? We'll mark our 2 pi out. I think we'll go the full 2 pi. But I'm going to go by pi over 4s this time because I think you get it. Or that, oh dear, I'm already contradicting myself. Yeah, oh, no, I just did it wrong here. Pi over 2, pi over 4, you know, we get 3 pi over 4, etc. So, cosine of 0. 0, the cosine of 0, well, if you look at the unit circle, you'll find that that's equal to 1. So let's start there. Now, cosine of pi over 4. Now, pi over 4 is the same as 45 degrees. That's part of an isosceles triangle. So, actually, the sine of that angle is going to be the same as the cosine of that angle, because the adjacent side and the opposite side are equal. So, the cosine of pi over 4 is going to be the same as pi over 4, which in the last video we found was about the square root of 2 over 2. In fact, it is that, exactly, which is approximately equal to 0.07. I'm sorry, 0.7. Oh dear. 0.7. 0.71. It's pretty close. So that's not really clearly a point. Alright, so let's graph that. That's going to be around here. Cosine of pi over 2. Well, that, if you look at the unit circle, is going to be 0. If you have pi over 2, essentially what you're saying is you have 2 right angles in your triangle, which sounds a bit silly. And it is a bit silly, but you're basically implying that one of the sides has 0 length. And, you know, technically you could claim that that's part of a triangle because it's, you know, it's part of the trig, but, you know, it's not really, it's more of a line. But anyway, when you calculate it, cosine of pi over 2 is equal to 0. Now we go another pi over 2, 3 pi over 4. So pi over 2, let's quickly do that. 3 pi over 4. I think I'll just go to pi and then fill in the rest, because I think you'll start to see the pattern. So 3 pi over 4, that's going to be another pi over 4. But this time, because we're doing cosine, once you go past the 90 degrees, if you look at a unit circle, I might just draw one here. You use the x-axis and the y-axis to determine sine of theta and cosine of theta, or cosine of x and sine of x in this situation, because the unit circle has a radius of 1, and so to find the distance of any given side, you'd find the sine of theta times 1, so for this side, say. So this side is going to be equal to sine of theta, because as we know, the sine of theta is just a ratio for the opposite of this angle to its hypotenuse. So if the hypotenuse is 1, we're going to find that the sine of this angle, in this case x, is going to be the y-coordinate of this, and that the x-coordinate is going to be equal to cosine of that angle. But we went over all of that in the unit circle video, so if you don't remember it, please recall that. So once we go another pi over 4, past 90 degrees, we're getting into negative cosines. So it's going to be the same as pi over 4 on the other side, but it's going to be negative. So instead we're going to have that be negative square root of 2 over 2, which is approximately equal to negative 0.71, which is going to be down here. We'll mark our 1. Negative 1. And we get to pi, cosine of pi. You probably know this well, and can probably hear my dog sneezing, which is a bit weird. So the cosine of pi is going to be equal to 1. I'm sorry, -1. What? Because we're on the other side of the x-axis. It's just like on this side, we have a 0-degree angle at pi. When we have pi, we've gone all the way around, and essentially we have a 0-degree angle from the x-axis. And that's just going to give us a cosine of 1. Again, we're doing a kind of silly thing where we're pretending that a line is a triangle. But that's okay. Just review the unit circle videos if this is confusing at all. But the cosine of pi is -1. Alright, now let's look at the pattern that we're starting to form. So like in the last video, I'm just going to kind of fill this in how I think it might curve based on how it looks. And I'm also going to assure you that this is actually what the graph looks like if you put it in a graphic calculator, or if you were to be really committed and plotted a lot of points, it would be a lot more clear. Obviously, you can't plot an infinite number of points on here to find the full graph, but if you plotted a lot, it would be pretty clear that this is the shape. So we're getting a similar thing as we did in the video where we showed the function as the sine of theta, and that is true. This is another wave, and it will continue like this, and it will continue up until it gets to 2 pi. I'm going to run into this stuff, though, so I'm not going to do that. But it is a wave, just like the wave in the sine of theta video. And I might actually pull that up quickly, just to get a little idea across. Just to make everything kind of satisfying. So what did our sine wave look like? It looked kind of like, right, it was 0 at 0, and it came up at pi over 2. But it was essentially the same wave. It was just shifted, right? Yeah. Yeah. It was shifted. So, how can we... Oh dear, something just happened. Go away. Go away, how dare you. Now, how do I get rid of this? Go. You probably can't see it on your screen, but some crazy thing just attacked my menu. I'm just going to push it out of the way so I can get back to work. Alright. So, this is essentially the same, but it's shifted over, right? How much is it shifted over? Well, as you can see, it looks like it's been shifted over, well, when is this function at its peak? Pi over 2. And when is this function at its peak? That's 0. Oh, there's a little weird line here. I might just want to get rid of that. There we go. Alright, so it looks as if the function's been shifted over. If we say this is our g of x, a new function, I might want to use a new color for that, because we actually used green in the last video, so that fits, is equal to the sine of x, and we have this function here. I'm just going to outline it in green. And it's essentially the same wave, but it looks as if it's been shifted over by pi over 2. So how could we write a relation between these two? Well, let's say we said, we're going to take the angle here. So we're going to have the sine, let's make a relationship. So we're going to have the sine of x, and we're going to kind of write a relationship to the cosine. So it looks like the cosine of... It looks like we've had... I'm going to write in another parentheses, and you'll see why in a moment. It looks like what we've done is, first of all, we can shift the angle over by 90. And how do you shift it over? Or by, 90 degrees, which is equal to pi over 2 radians. We can shift it over by that much. And how do you do that? Well, what you do is essentially you take whatever your x variable is, your input variable, and you subtract that constant, right? Because now, to get the same answers with x has to be pi over 2 greater. This is essentially shifting everything over by pi over 2. But, that doesn't help much because now we have a graph like this. It looks like the opposite wave. And that's just right. I'm going to erase this. So we essentially have the opposite wave up here. I'm drawing it a little short. So essentially what we're doing is, what we need to do, and this is getting quite messy now, is flip that over. So now we take the negative of that, and we get the sine of our angle x is equal to the cosine of, when we multiply the negative out, when we distribute it, we get the cosine of pi over 2 minus x. So they're basically the same wave, but they're shifted over, just like this. And to show that this is correct, let's look at a triangle. So a right triangle, obviously. So we have some angle here. We're going to call this x, right? Right, yeah. And then we have our other angle, theta. And let's write some of the sides. Let's call this C, A, and B. What's the sine of x? Well, the sine of x, hopefully you can see this all quite nicely, is going to be, right, opposite over hypotenuse. So katoa, it's a ratio. So that's going to be B over C. Now, what's the sine of theta? Well, sine of theta is going to be equal to A over C. But what's the cosine of theta? Well, the cosine of theta, cosine of this angle theta, is also equal to B over C. Right? So now we just, well, what is theta equal to in terms of x? Well, in a right triangle, and I'm going to start clearing some of this away so that we can get our nice space. Oh dear, I didn't really want to clear away that, but I'll have to do. Over B. In a full triangle, we have 180 degrees, or we have pi radians. And that's going to be equal to our x plus our right angle, which is pi over 2 radians, plus our theta. And so we can isolate the variables here by taking pi over 2 to the other side. So we have pi over 2, right? Pi minus pi over 2. It's half of pi. It's going to be equal to x plus theta. And you can probably see where this is going, because now we have that theta is equal to pi over 2 minus x, right? And so now we have, right, because sine of x is equal to the cosine of theta, sine x is equal to cosine of theta, which is equal to, we plug that in, cosine of pi over 2 minus x. Oh dear. Now, it's getting really messy now, but as you can see, that's the same result we got over here. So that's correct. They're basically the same wave, but they're shifted over. So this is the cosine function. In the next video, I'm going to talk about the tan function, which is a little bit special. And of course, there's all the others like secant and, cotangent and, things like that. But we're not going to be going over those because they're inverse functions and they're kind of less integral to your understanding at this point. All right, thanks for watching.